older farmhouses where a visible ground rod is absent, establishing proper ground is essential for electrical safety. The absence of a visible ground rod near the power entrance to the house necessitates alternative grounding methods. Firstly, investigate the water line. If the water line entering the house is made of copper or another metal, it can potentially serve as a grounding electrode. To utilize the metal water line, connect a copper or aluminum ground wire to the water line inside the house. This connection should be made near a plumbing fixture or the water heater for optimal effectiveness. Secondly, if the water line is constructed of plastic, which is non-conductive, you will need to explore installing either a grounding ring or a driven ground rod. A grounding ring involves burying a copper or aluminum ring around the exterior perimeter of the house. This ring must be buried at a minimum depth of 2 feet in soil that remains permanently damp to ensure effective grounding. To complete the grounding ring installation, connect a ground wire securely to the ring. As an alternative to grounding ring, a driven ground rod can be used. This involves driving a copper-plated ground rod into the soil to a depth of at least 8 feet. The location for the ground rod should be chosen carefully, ensuring it is away from any electrical equipment or buried pipes to prevent interference or damage. Once the rod is driven to the required depth, connect a ground wire to it. Thirdly, if the house incorporates metal framing or structural steel, this can also be utilized as a grounding electrode. In this case, connect a ground wire to an exposed section of the metal framing or structural steel to establish the grounding connection. Fourthly, consider installing a grounding plate inside the electrical panel. The grounding plate is a copper or aluminum plate equipped with multiple screw terminals specifically designed for grounding connections. This plate allows for convenient and organized grounding of various electrical components. Fifthly, regarding neutral grounding, it is important to note that in some older electrical installations, the neutral wire may have been used as a grounding conductor. However, this practice is strictly prohibited by modern electrical codes due to its inherent safety risks and unreliability. Therefore, relying on the neutral wire as a grounding conductor is not a recommended or acceptable method. When installing the ground wire, it is crucial to use a minimum of number 8 American wire gauge, abbreviated as AWG, bare copper or aluminum wire. This ensures adequate conductivity and mechanical strength for the grounding connection. Run the ground wire carefully along the exterior or interior of the house, ensuring it remains separated from power lines and other electrical conductors to prevent potential hazard. Finally, connect the ground wire securely to the grounding conductor terminal inside the electrical panel. This terminal is typically identified by a green color or a bare wire. Regular inspection and maintenance of the grounding system are essential for ensuring its continued effectiveness over time. It is highly recommended to consult with a licensed electrician to ensure proper grounding practices are followed and electrical safety is maintained. Remember, grounding is a critical aspect of electrical safety, and improper grounding can lead to dangerous situations. Proper grounding ensures that electrical faults are safely directed to the ground, minimizing the risk of electric shock and fire hazards. The grounding system provides a low impedance path for fault currents, allowing protective devices such as circuit breakers to quickly trip and disconnect the power supply in the event of a fault. This helps prevent damage to equipment and protects individuals from electrical hazards. There are several types of grounding systems commonly used in residential and commercial buildings. These include the equipment grounding system and the system grounding system. The equipment grounding system provides a path for fault currents from electrical equipment back to the source, while the system grounding system grounds the neutral conductor of the electrical system to earth. The National Electrical Code, abbreviated as NEC, provides comprehensive guidelines for grounding and bonding electrical systems. Compliance with the NEC is essential for ensuring electrical safety and preventing electrical hazards. The NEC specifies requirements for the size and type of grounding conductors, as well as the methods for connecting grounding electrodes. Grounding electrodes are typically made of copper or steel and are buried in the earth to provide a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. Ground rods are typically driven into the earth to a depth of at least 8 feet and are spaced at least 6 feet apart. Ground plates are buried in the earth and provide a larger surface area for contact with the soil. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of an electrical system together to create a low impedance path for fault currents. This helps to ensure that all metal parts are at the same potential, reducing the risk of electric shock. Bonding conductors are typically made of copper and are connected to metal enclosures, conduit, and other metal parts of the electrical system. The size of the bonding conductors must be adequate to carry the maximum fault current that could occur in the system. Proper grounding and bonding are essential for protecting people and property from electrical hazards. It is important to have a qualified electrician inspect your electrical system regularly to ensure that it is properly grounded and bonded. If you notice any signs of electrical problems, such as flickering lights, sparking outlets, or tripped circuit breakers, you should contact an electrician immediately to have the problem diagnosed and repaired. Grounding is also important for protecting sensitive electronic equipment from damage due to voltage surges and other electrical disturbances. Voltage surges can occur due to lightning strikes, power outages, or other electrical events. These surges can damage electronic equipment if they are not properly grounded. Surge protectors are devices that are designed to protect electronic equipment from voltage surges. Surge protectors typically have a metal oxide varistor, abbreviated as MOV, that diverts excess voltage to ground, protecting the equipment from damage. It is important to choose surge protectors that are rated for the voltage and current requirements of the equipment being protected. Surge protectors should also be installed properly, following the manufacturer's instructions. In addition to grounding, other electrical safety measures include using ground fault circuit interrupters, abbreviated as GFCIs, and arc fault circuit interrupters, abbreviated as FSIs. Ground fault circuit interrupters are devices that are designed to protect people from electric shock. GFCIs monitor the current flowing in a circuit and trip the circuit if they detect a ground fault. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are typically installed in bathrooms, kitchens, and other wet locations where there is a high risk of electric shock. Arc fault circuit interrupters are devices that are designed to protect against electrical fires. FSIs monitor the current flowing in a circuit and trip the circuit if they detect an arc fault. An arc fault is a dangerous electrical condition that can cause a fire. Arc faults can occur due to damaged wiring, loose connections, or other electrical problems. FSIs are typically installed in bedrooms and other areas where there is a high risk of electrical fires. Electrical safety is a shared responsibility. Homeowners, landlords, and contractors all have a role to play in ensuring that electrical systems are safe. Homeowners should have their electrical systems inspected regularly by a qualified electrician. Landlords should ensure that their rental properties are properly grounded and bonded. Contractors should follow all applicable electrical codes and standards when installing or repairing electrical systems. By working together, we can create a safer electrical environment for everyone. Furthermore, it is crucial to understand the role of grounding in surge protection. Surge protection devices, or SPDs, rely on a properly grounded electrical system to effectively divert excess voltage caused by lightning strikes or power surges. Without a reliable ground connection, the SPD may not function as intended, leaving your valuable electronics vulnerable to damage. When evaluating your grounding system, consider the soil conditions in your area. Soil resistivity can significantly impact the effectiveness of a grounding electrode. Sandy or rocky soils tend to have higher resistivity than clay soils, making it more difficult to achieve a low impedance ground connection. In areas with high soil resistivity, it may be necessary to install multiple ground rods or use chemical ground rods to improve grounding performance. Chemical ground rods contain chemicals that leach into the surrounding soil, reducing its resistivity and enhancing the ground connection. The NEC specifies requirements for the maximum resistance to ground for grounding electrodes. The resistance to ground should not exceed 25 ohms for a single ground rod. If the resistance exceeds 25 ohms, an additional ground rod must be installed and connected to the first ground rod. The two ground rods must be spaced at least 6 feet apart. The NEC also allows for the use of other types of grounding electrodes, such as ground plates and concrete-encased electrodes. Ground plates are typically made of copper or steel and are buried in the earth to provide a low-impedance path to ground. Concrete-encased electrodes, also known as UFA grounds, are made of steel reinforcing bars that are encased in concrete. UFA grounds are typically used in new construction and can provide excellent grounding performance. In addition to grounding electrodes, bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of an electrical system together to create a low-impedance path for fault currents. This helps to ensure that all metal parts are at the same potential, reducing the risk of electric shock. Bonding conductors are typically made of copper and are connected to metal enclosures, conduit, and other metal parts of the electrical system. The size of the bonding conductors must be adequate to carry the maximum fault current that could occur in the system. The NEC specifies requirements for the size of bonding conductors based on the size of the circuit conductors. Proper grounding and bonding are essential for protecting people and property from electrical hazards. It is important to have a qualified electrician inspect your electrical system regularly to ensure that it is properly grounded and bonded. If you notice any signs of electrical problems, such as flickering lights, sparking outlets, or tripped circuit breakers, you should contact an electrician immediately to have the problem diagnosed and repaired. Regular maintenance of your grounding system is also important. Over time, grounding connections can corrode or become loose, reducing their effectiveness. It is important to inspect your grounding system periodically and tighten any loose connections or replace any corroded components. You should also test the resistance to ground of your grounding electrodes periodically to ensure that they are still providing a low impedance path to ground. Testing the resistance to ground can be done using a ground resistance tester. A ground resistance tester is a specialized instrument that measures the resistance between a grounding electrode and earth. The tester works by injecting a current into the earth and measuring the voltage drop between the grounding electrode and a reference electrode. The resistance to ground is then calculated using Ohm's law. When testing the resistance to ground, it is important to follow the manufacturer's instructions carefully. The tester should be calibrated regularly to ensure accurate readings. The test should be performed under dry conditions to avoid inaccurate readings due to moisture in the soil. The results of the test should be documented and compared to previous readings to identify any changes in the grounding system's performance. If the resistance to ground is found to be higher than the NEC limit of 25 ohms, corrective action should be taken to improve the grounding system. This may involve installing additional ground rods, replacing corroded components, or improving the soil conductivity. Grounding systems are an essential part of electrical safety, protecting people and property from electrical hazards. Regular inspection, maintenance, and testing of your grounding system can help ensure that it is functioning properly and providing the necessary protection. In addition to the physical components of a grounding system, it is also important to understand the principles of grounding and bonding. Grounding is the process of connecting electrical equipment and systems to the earth to provide a low impedance path for fault currents. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault currents. The purpose of grounding and bonding is to minimize the risk of electric shock and fire hazards. When a fault occurs in an electrical system, such as a short circuit, current will flow through the grounding and bonding system back to the source. This current will cause the protective devices, such as circuit breakers and fuses, to trip, disconnecting the power supply and preventing damage to equipment and injury to people. Without proper grounding and bonding, fault currents could flow through unintended paths, such as through a person's body, causing electric shock. Fault currents could also cause fires by igniting flammable materials. Grounding and bonding are therefore essential for electrical safety. The NEC provides detailed requirements for grounding and bonding electrical systems. These requirements are based on years of experience and research and are designed to ensure the safety of people and property. It is important to follow the NEC requirements carefully when installing or repairing electrical systems. If you are not familiar with the NEC requirements, you should consult with a qualified electrician. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself from electric shock and other hazards. Always turn off the power to a circuit before working on it. Use insulated tools and equipment. Wear appropriate personal protective equipment such as gloves and safety glasses. If you are not comfortable working on electrical systems, you should hire a qualified electrician to do the work for you. A qualified electrician has the training and experience necessary to perform electrical work safely and correctly. Electrical safety is a shared responsibility. By following safe electrical practices, we can all help to prevent electrical accidents and injuries.